Yeah, good morning, everyone. So, as our first speaker, we have Gabriele from ETH, who will continue his lecture on hydrodynamics of classical quantitative systems.
Thank you. Thank you. Good morning for everybody. I know it's morning and we are approaching the end of the week, so I will try to keep it light. And we continue along the lines we were discussing last time. In particular, we were discussing how to obtain an efficient description of the thermodynamics properties of integrable systems. We were interested in thermodynamics properties because we saw that these are essential inputs necessary to write down Euler equations, so hydrodynamic equations at the largest scale, which is called Euler. We considered as an example, as a paradigmatic example, this classical gas, which is called Toda gas, where you have particles, momentum, non-relativistic, and then some interaction. And we discussed how to, since we are interested in thermodynamics, we wanted to compute the partition function for canonical equilibrium or generalized equilibrium state. So this W of P is something like this. So this encodes the generalized equilibrium maximal entropy states because it contains all the multipliers with high inverse temperatures associated to this state, and these are the associated single particle eigenvalues. Okay? For instance, this one, for number of particles, index I equals 0, this is 1. For kinetic energy, let's say I equal 2, this will be P square over 2, for instance. For momentum is P, just to give some example. Okay, and it's here. And we saw that for integrable models, an efficient, good basis to write the partition function to perform calculation that now we finish is the basis of scattering states. In particular, we express the partition function in terms of the scattering states in the asymptotic past, so minus infinity. And this was good because in terms of these states, you see, in terms of the Boltzmann weight, so exponential of minus the sum of the multipliers times the charges is pretty simple. It takes the form that it takes for free particles. The complicated part, let's say, is entirely in this integral here over space. This is an integral over the volume in the asymptotic space coordinate, constrained on the coordinates on the initial time slice being in this volume where the system is initially confined, okay? And we saw that to compute this integral, because now all the complexity of the problem is hidden here, the part with momentum, let's say here, is simple enough because it's free particles. It's important to relate the volume that in asymptotic coordinates to the one in the initial time slice. And in particular, we found this expression from the scattering theory, where the volume L on the initial time slice is related to the volume R in the asymptotic coordinates by this relation, where phi is the two-body scattering shift, which depends on momenta. And therefore, the transformation from R to L, and vice versa, is momentum dependent. Okay? This is where we ended up last time. Do you have questions, comments? Otherwise, we continue along this line. So, in particular, this integral here, this one here that is framed, this one will be equal to the volume in asymptotic coordinates to the number of particles, because it's an n-fold integral running over the number of particles. And here we express this R in terms of L using this relation here. And therefore we get this stuff here. Just plugging that equation over there inside here. And now we insert these into the partition function. Okay, and we get as usual, you stop me anytime if you have questions. Yes, that's correct. Should be fine with parentheses. So here I'm just exponentiating to put everything into the Boltzmann weight, this factor here within the product. And yes, and then I have this factor L to the n, which comes from here. That's okay. Now, as usual, we want to take thermodynamic limit. This whole story is because we want to derive thermodynamics in the thermodynamic limit for this system. So thermodynamic limit, we define it like the initial volume that we take it to infinity. So we take that the initial gas is in a volume which can be infinitely large. The number of particles also is consequently taken to infinity. We fix the ratio. Let me call this 1 over rho. This is a rho. Just to say it's 1 over density, because you see it's a volume divided by number of particles. Sounds good? So this is the standard way you define thermodynamic limit. So you scale up the size of your system, the number of particles as well, keeping the ratio, which is the density, finite. Okay? And now we use a trick which is very useful in statistical physics, and it's essentially as old as Boltzmann, because we define what is called the empirical density. And we define it this way. Let me call it, now I have to avoid making a mess with the notation. Let's see.
Sorry, I was confused. When you write this EXM, when you write this measure, you calculate this integral, is that PM minus infinity, but when you substitute
No, this is still PM minus infinity, sorry, and I forgot it.
So before PM minus infinity, before the particle was confined in a volume 0 to L, and now they are in 0 to R.
In the asymptotic coordinates, yes.
The asymptotic, they're 0 to R, and then, okay.
Is it fine? Yeah, here I forgot the minus infinity, thank you. Inside the partition function. So the empirical density, I write this rho subscript P, so density of particles, and I define it this way.
My confusion remains.
I think that in thermodynamic limits is fine, no? Because you assume that you take an infinite volume, so it's not anymore confined. I think maybe in this way you have a good way to take thermodynamic limit. This was what I was thinking.
So why would I be interested in computing the partition function?
Because you want statistical fluctuations for a system infinitely large. Well, but if you need in an infinite volume, yes, because they are not anymore constrained, so they can stay everywhere.
No, so initially they are here, and eventually they will go to Venus. I mean, as a mathematical quantity, it is well defined, but as a physical quantity,
Maybe we discuss later, so that maybe because otherwise I run late, but later we discuss indeed. I just define empirical density like this now. This 2 pi factor is convention, so no deep physical meaning. But you see it's 1 over L, then the sum over the delta of P minus Pn. So essentially this counts the density of particles in an interval between P and P plus dP, okay? So that when you take the thermodynamic limit, something like that, we assume that, as usual in stat phys, this object becomes a smooth function of the momenta, of the phase space coordinate, so that for every function, f, let's say generic function, of the momenta, okay, the sum over n scaled by L can be replaced, let's say, in thermodynamic limit. Yeah, right, T edge lim is a thermodynamic limit, can be replaced by the integral of the same function weighted by this density, okay?
So this is now the quasi-particle density?
It will become the quasi-particle density eventually. This is why I put the subscript P, because it's particle density, and also to distinguish from this rho. If I forget it, remind me. I'll try to be consistent. But this is like when in statistical mechanics, for instance, in the Boltzmann-Edge theorem and so on, you define a density in phase space coordinate. Now, the phase space, I label it only with P because we are taking an homogeneous system at the moment. We are in the thermodynamics, so there is no X space dependence. It will come later. And then, of course, we want to write now this partition function in terms of this density. Oops, too strong. Yeah, here the argument will be all the asymptotic momenta. You can put minus infinity. Now, I want to do. Okay. Now, if we rewrite the partition function in terms of rho, this will become essentially a functional integral. So I write it with the functional measure, which is the capital D. And then it's the exponential of minus the volume, I, which is taken to be very large, times a functional of the P. I'm just already forgetting the subscript. And now I write the I to be complete. Just finish the writing and then I explain you the meaning of the terms, even though it's quite clear. I finished the blackboard. Yeah, just 1 second, I copy the equation, otherwise I do a mess. No, times I'm sorry, here I was just finishing the width of the blackboard. This is integral Q phi P minus Q times rho P of Q. Then this parenthesis here closes the argument of the log, and this square brigger parenthesis matches this one. Yes, you had a question.
Just what is actually so that dxn integral, volume integral, that was the R.
And R we wrote it in terms of L.
What was the notation like?
Because because there you have the integral, you see the squared, the framed integral, and fold over xn minus infinity coordinates. It's an integral in the volume space in the asymptotic coordinates at minus infinity, but it's constrained because you see these asymptotic coordinates must be chosen such that in the initial time slice you stay between 0 and L. So you have this constraint. So in order to write it, we have to express R in terms of L, where this is the relation that we derived last time. And in the end, since you have this constraint that xn belongs to 0, L, the integral becomes dependent on L. Indeed, you see here, there is L.
In your second equation, after the defining the density, yes, you mean to say that any function of the momentum can be written as a
Smooth function, yes. In the thermodynamic limit.
You wrote rho, so I was confused.
This is an F. This is an sorry, this is an F and this is also an F.
Okay, fine, that's what I was thinking.
You had another.
There can be this empirical density part in this experiment.
Yeah. This is just essentially you define in thermodynamic limit this object, which is like a density of particles in a cell of length here, infinitesimal dp of the phase space. This is like the density in phase space, which since we have an homogeneous system at the moment, is thermodynamics, purely homogeneous, is only momentum dependent. When you do hydrodynamics and you upgrade it with space, this will have also an X, so it will become a density in phase space. And you define it such that, this you see, this is purely the microscopic definition because it counts for each, at a given momentum in a given phase space infinitesimal cell, how many particles you meet with this delta function. 2 pi is just a convention, I put it. And in the thermodynamic limit, this TH lim, you take that for every sum of a smooth function of the momenta, this can be replaced by the integral of the associated function weighted with this density in phase space. And when you do this, essentially the integral that you get is of this form, where this I is expressed this, and this you can read it essentially from here, because you see there is a W, then there is the log, which is here, which becomes the log of, and then you see here you have a sum, 1 over L, and it's converted as an integral over 2 pi, weighted by this rho, okay, according to this prescription here. And then we have also this factor here, this -1 comes from Stirling approximation of this factor, L to the n factorial, if you do the Stirling approximation of the factorial for large n. Because in the end you want to extract the extensive part of everything, right? Because you are interested in thermodynamics and you want to define densities which are well defined, so upon dividing by the volume. So you want to extract this factor, everything. And there is just this guy, which maybe you are wondering about, which is not present in the line above. And this essentially comes exactly from this definition, because when you introduce this density, you are already coarse-graining a bit, because you pass from a description in terms of microstates, which are labeled in terms of momenta, asymptotic momenta, to a macroscopic already description in terms of densities. Already this comes with an entropy, because you have multiple microstates, which correspond microscopic arrangement of the momenta in a given phase space cell dp that correspond to the same density rho p, okay? This is an entropic factor, which for a classical gas, not surprisingly, takes the log rho form. This is actually, you can do it as a simple calculation. It's one of the first calculations of, we can also discuss it in tutorials if you want, but it's very simple. It's like a Boltzmann counting calculation, where you partition your phase space into cells, and you count how many particles in a given cell of length dp are there, consistent with a value of rho p. And you see that for classical systems, you get this log rho. Okay, so this is an entropic term. All the other terms, you can read them directly one-to-one with the expression above, okay?
You're not, so in your last expression, you said the log, the last log. These are all at the asymptotic limit, right? Your momentum certified asymptotic.
Yeah, in the asymptotic coordinates, you're right, indeed. And in this way, you write this partition function in this form. We are taking thermodynamic limit. So how would you evaluate this kind of integral in thermodynamic limit? Suggestions, comments? Saddle point, yes. Saddle point is the crucial approximation of all statistical physics. Spoiler. Because when you take thermodynamic limit, this integral will be concentrated on a typical configuration, rho p of the particles, which minimizes this functional I. This functional I, actually, you see, and therefore, let's say, exactly. So you look for the optimal configuration that minimizes this functional I in the thermodynamic limit. And here I write this symbol because this means equality up to sub-extensive terms, because you want to extract only the part which is here leading in L. This is like this is large deviation form, if you know large deviation theory, okay? And in particular, this tells you that if you compute I rho p star, this will be equal to minus limit over L to infinity 1 over L log of Z, okay? Just inverting this. And this is the, what is this? Minus 1 over L log of Z. Free energy, exactly. So this is the free energy density. So in principle, in this way, we can finally compute the free energy density, which is our goal to quantify all thermodynamics properties. Now, this calculation, you can do it is a variational calculation at this point, because you have to do functional derivative of all of this functional capital I that I wrote here. There are some steps. I think the steps are contained in the notes. I won't report them because for brevity, but in the notes, I think you can all access the notes right from the website. On the notes, you can also find the mathematical steps. In the end, it's just algebra. It's not deep variational calculation. And you can see what this equation boils down to and what is the expression for the free energy. Here I write the result that, with some calculation, you get that the free energy density, because it's scaled by volume, can be written in a form which is pretty much clear. So this is over asymptotic momenta, as usual. And this function here, this is an epsilon, okay? This function epsilon is this form. Now, interpretation. Okay, this is the free energy density. And we write in terms of this epsilon. This epsilon, you see, it satisfies this equation here, below. That is a nonlinear integral equation, because the epsilon appears here and also here inside an integral and inside a nonlinear function. In this case, this exponential, okay? So this is a nonlinear integral equation. It depends on this WP, which is what we defined at the beginning, is this object. I just write it again for completeness. So this WP contains the inverse temperatures. So this WP contains the information about the state, the thermodynamic state you are, Wolff's fluctuations, equilibrium fluctuations you are studying. Mu is chemical potential. Is the chemical potential that we introduce to fix the density, so that we have that the integral over the asymptotic momenta divided by 2 pi of rho, the density of quasi-particles in rho p. This is equal to the density that we are prescribing, okay? This rho is a number, let's say. You come to me, you tell me the density of the gas is 0.7, and the chemical potential is fixed so that the integral of this density in phase space gives the prescribed density, 0.7, okay? So this is a multiplier, chemical potential, it has the meaning. And then you have this object here. And the interpretation is that, imagine you don't have interactions at all. So if you don't have interactions, there is no scattering among these tracers, these quasi-particles. This term is not there, okay? And this tells you that this epsilon has the meaning of essentially the Boltzmann weight that you have there minus the chemical potential. And this is called bare, let's say, energy. So it's the energy that would characterize the system without interactions, okay? I mean energy in quotes because in principle here there can be also other multipliers rather than the temperature. If you have only the temperature, let's say, for a purely thermal case, this Wp is beta 2 H2 of P, so this is beta 2, which is the inverse temperature, P square over 2, okay? So you see it's the temperature times the bare energy, P square over 2 of a quasi-particle. This is the standard form of kinetic energy. But since you have interactions, this quasi-particle with the momentum P interacts and scatters with all the other ones, Q. There is a collective effect. And this gives rise to this integral which dresses this bare value to give something which is renormalized energy dispersion relation by the interaction. This is the interpretation. And this one is what appears here, inside to compute.
So this WP is the kinetic term, as you mentioned.
This WP is?
Is the kinetic term. Kinetic term.
This is for a purely thermal case, where you have only the multiplier beta 2, so the inverse temperature associated to energy, second charge, so beta 2 P square over 2.
So I didn't get this thing. So you're telling me that when I integrate over the mu term, when I integrate over the phase space, I get a total number density. So this is the total number.
This is the density, yes, your density.
Total density. And that will fix me for
This equation here, mu is chosen so that this is satisfied. Then, in this way, mu is a chosen parameter, and then you have to solve this integral equation, which is a closed equation, which you can solve by, in general, numerical methods, because it's not analytically solvable, iterative means. There is exercise number 2 of the tutorial, which I think gives one specific example where you can try to implement the numerical solution of this and explain the physical meaning of your result. This we will discuss it in the tutorial to make this more practical and evaluate it specifically in a case, which is always good to get more intuition. Is this clear?
What's the form of this Q? Because it's self-consistent.
It's self-consistent, yes. Q is a coordinate, is momentum, asymptotic momentum in principle. And so it's a closed integral equation that you have to solve. In general, here it's by iterative means. So you start with an initial guess that maybe is this bare value. Then you plug it here. You compute this object. This gives you an updated value. And then you iterate until you get convergence. This is the scheme that we follow. Yeah, please.
So earlier your WP involves all the beta i's, but when you go from the beta to beta.
It's to give an example. This is an example. Is an example that is also the example that we will discuss in the tutorial, just to give an example of a purely thermal state where you have only temperature. In general, it can include also others. And with this, now we are done, because now we have all the tools to describe the thermodynamics of integrable models, because we have a free energy, pseudo energy. Yeah, this is called the pseudo energy. And we have the density, rho p, of particles. So in particular, now just a bit of definitions. Now, these calculations, we have done it for Toda chain, but actually is completely general and applies to all integrable models, thermodynamic by the ansatz integrable models, modulo inserting as input some information that now I clarify. So, free energy density, we will write it as, I drop just the minus infinity on the momenta now, something like that. I define, now it's just a moment where we define some objects that will be relevant. Phi. Now, this is the free energy density, and we write it with this function capital F. This function capital F depends on the statistics, quantum classical statistics of the particles. Let's say, and this is an input that you need to give. So whether you are describing a classical gas, a fermionic gas, a quantum gas, or something else, here the statistics enters and determines the form of this function capital F. I give examples. But the form is not surprising, I would say. So for instance, for a classical gas, like the Toda chain, you see there is exponential of minus epsilon for this function that we can read from there. If you do the same calculation, thermodynamic by the ansatz, but for fermions or bosons, I will write a reference now that we are done. For instance, for fermions, this function capital F, not surprisingly, is this. It's minus log of 1 plus the Boltzmann weight. This is like the partition function of a free Fermi gas. For bosons is this one, which is like partition function of free Bose gas. The trick with integrable model is that they look as quasi-free because they take similar form as the free case, but everything is dressed on top of this. So this is the free energy of a free gas, but the argument epsilon is this pseudo energy here, which is dressed by this integral, by the collision with all the other quasi-particles. Okay? But this form of the F is what you need as input and what specifies the statistics of the quasi-particles of the model you are interested in. Okay? Which one? The Bose? You have let me see. I copied, yes. Yeah, is log of 1 minus exponential E of minus epsilon. This is exponential, E to the minus epsilon. Yeah, there was a mistake, sorry. And then, okay, this is an input. Let's say, let me use colors. Then another input, of course, is inside the W. This is the W is, I just write it again. Sum over I which runs over the charges. This specifies the state you are considering, so the inverse temperatures beta I, which appear in the state, and the associated single particle eigenvalue. Of course, also the shape of the single particle eigenvalue depends on the model you might consider. Let's say for a non-relativistic gas, like Toda or Lieb-Lininger, for instance, kinetic energy is p squared over 2, okay? This is another input. Then there is, of course, the input here, the phi, which is the two-body scattering shift, which depends on the model studied. Let's say, for instance, for Toda, phi is equal to twice log of modulo P. For hard rods, this is momentum independent actually, and is equal to minus the length A of the rod. For Lieb-Lininger, this is, we wrote it last time, I'm just copying again. It's something like this. Where G is the interaction constant.
What is that rho total thing?
I'm coming to that, still not yet. So this is another input of the model, so the form of the scattering shift. And then we define this rho tot. This rho tot, it has an interpretation, which fortunately the blackboard is winding back exactly at the right moment, because you see that this rho tot, this equation here, integral equation, it's pretty similar to continuum limit of this. If you define L over R, probably I have it also here, you will see that L over R from here, it's equal to 1 minus this sum, which in the thermodynamic limit becomes the integral of this phi times the rho, the density of quasi-particles. So essentially this one, in the thermodynamic limit, becomes equal to the rho tot. So what is telling you, rho tot? It tells you essentially the mismatch between the volume in the original slice and the volume in the asymptotic space. So it's like a metric, because it tells you how the space the particles perceive is modified, changes, as a consequence of interactions, okay? Is this clear from this and this, how you match that equation?
I think these things sometimes interpreted as some whole kind of particle, quasi-particle, quasi-whole.
Sorry, tell me say again.
Is it kind of related to some quasi-whole, quasi-particle, that picture?
Yeah, exactly. Because this is like the change of metric, and this is like this is a momentum-dependent function in general. This is like the total number of states that are available. Then the total number of states that are available, you can decompose into particles, so the states that are occupied by your system. This is rho p, plus the holes, states that are empty, unoccupied. And you see now that I have written this, now you understand also the meaning of this n, because this is the fraction of particles, states that are occupied, divided by total number of states. So you see by the definition this object is smaller or equal than 1, larger or equal than 0. This is an occupation function in the phase space density. For a Fermi gas, this essentially is a dressed version of the Fermi sea. And just want to close one sentence. So this is the general structure of what is known as thermodynamic beta ansatz, TBA. TBA is essentially this set here of coupled nonlinear integral equations that describes the thermodynamics of integrable models. Then which specific model you want to study enters in the form of this input that we have highlighted in orange. This is the main bit I want to transfer of information. And yes, you had somebody had a question.
So for the total gas, you have this EP as WP minus mu times the bare energy times this two-body scattering. So,
And also for the other models, yes.
right, so
The structure is always this one.
right, so it's a generic structure for every mode. For
Every thermodynamic beta ansatz thermodynamic integrable model.
right. So where the statistics comes in, whether you are taking classical particles are your bosons?
Yeah, this comes in the form of this function capital F you enter, in the form of this for
Scattering will also be modified?
what the?
The two body scattering will also be modified?
Yes, indeed. You see here there are different examples. For Toda, for instance, it's this one. This phi here is this phi here. The form of the scattering shift depends on the model. Yes? HR? HR here is a short for hard rods.
No, I mean the expression I.
Of what? HI?
minus A.
Minus A. This is minus A, where A is the length of a rod. You have these segments with hardcore repulsion of the volume length in one dimension A.
I have a simple question. So, conventional equation answers then guaranteed to hold for integrable systems which are defined in continuum.
In continuum, momentum.
Yes. If, let's say if I take an integrable lattice system, even classical equation, I don't see that how can you define scattering theory for the
I mean, in the case, this is like if you take a lattice system, could be like Heisenberg chain, XXZ. Remember, this is valid in thermodynamic limit. You assume thermodynamic, you take thermodynamic limit so that you can define this function as a smooth function of the momenta, because it's the usual stuff where when you have a finite system, lattice, momenta are discrete. In the thermodynamic limit, they become dense, a continuum, and you can define a continuum density of momenta in a certain interval. And from this density, then you can construct this kind of stuff.
See that the structure of the solution is always going to look like this. For your expression of T and its density, and it's always has to have that kind of particular form. I mean, I understand for total lattice it's the equation that you give, but I do not see simple reconciliation for discrete things.
Discrete things, I mean, they require some work. It's like how you get, for instance, for XX, Heisenberg, XXZ, I mean, this is maybe what you are interested in. It passes through what is called, you start from a wave function, you introduce a vacuum, for instance, for XX, which is the completely down. You introduce Magnon, I think it's related to what Chiara was explaining in her course. You introduce Magnon excitation on top. This defines the coordinate beta ansatz, which is the wave function describing the many-body state for this discrete spin chain. And then you have a set of beta equations for finite volume. And then when you take thermodynamic limit, these beta numbers, which labels the solution, become dense. You describe in terms of a density. And the partition function, which is written as a sum over discrete quantum numbers, you replace it with a functional integral. And this is more or less the story. And now, indeed, I want to write a reference so that you have, where this is discussed also for other models than the classical Toda. I have it written here. Just 1 second. I write the reference, and then I ask you. I reply. So for this class of Toda system, I think a reference is this one. This discusses the case of the Toda gas. It's more written in a bit more mathematical format language. It's Journal of Mathematical Physics. Here I tried to digest it in a way so that it's understandable also for more physics-oriented public. But this discusses specifically the case of the Toda chain. And then I will say, to reply your question, how you construct these densities also for discrete integrable model spin chain, or for instance for the Lieb-Lininger. In this case, one reference that I like a lot is this one. It's from Franchini. It's a book. It's called, I think, Introduction to Integrable Models in One Dimension. In one dimension. It's a book from Springer, but it's also available on arXiv as a preprint. So you can find it also on arXiv. This is an excellent book, I would say. It's very clear. And in particular, in chapter 2 of these, you can find the thermodynamic Bethe ansatz. So similar calculations are these for the Bose gas, so for this case here of the Lieb-Lininger. Then chapter 3 has, for instance, the XX Heisenberg chain or XXZ. And in particular, in chapter 5 here, you also find the algebraic Bethe ansatz, so the construction that Chiara was explaining you with the monotomy matrix, lax operators, Young-Baxter, etc. So this is a good point to start. One dimension. In archive is not written 1D, it's written one dimension, but Fabio Franchini, yes. You find it also on the archive as a preprint. Now it's published as a book in Springer. Okay. There was somebody with a question, I think.
So you have this energy from this end part, and now what if you get the self-consistent integral equation of the energy, and you also get the rho hat, and what's the last one?
N. This is N. This is like, you see, is the fraction between occupied states and total number of available states. So it tells you the percentage, the occupation function in momentum space. Because you see rho tot decomposed in terms of density of occupied states, particles, density of unoccupied states, holes, and this is the fraction of the particles divided by the total. This N.
How do you calculate the density of occupied states?
I mean, in principle, what you should do is, this is also what is asked in exercise 2, when you see this stuff. I mean, you start from this, right, which is an equation for epsilon. You solve it, and then you have epsilon. Then, from epsilon, you can get n, because the form of n, yes, maybe this I have not written, but n is related to epsilon. For instance, in the case that you see in the Toda chain, n is something like this. Exponential of minus epsilon times 2 pi. And this is, for each kind of statistics, Fermi, classical, Bose, n has a different functional dependence on epsilon, but known. I am saying that this one here, n equal to minus e to the minus epsilon over 2 pi, if you insert it here, you get that.
2 pi f epsilon.
Huh?
2 pi capital F epsilon.
I'm saying that this n, this is 2 pi capital F, yes.
It's the general.
No, it's for Toda. For Toda. This I'm just giving an example for Toda. But exactly, what I can write in general is that the general relation is that n is related to F in this way. So if you know the function capital F, which is one of these three, let's remove this one, which does only a mess here. N of P, which is momentum, it's derivative of the capital F with respect to epsilon, evaluated at epsilon of P, where epsilon of P is the solution of this. Okay? But the take-home message, apart from the detail, is that from this capital F, you know the functional dependence of n on the function epsilon. So the way you determine all the densities is that you start from this, you solve it numerically, in general, you determine epsilon, then from epsilon you have n, okay? From n, you can write the particle density in terms of the total density from this relation. This you plug it here, then you have a closed equation for rho tot integral. You solve it for rho tot, and then from rho tot and epsilon you can determine p and holes. It's a closed set of integral equations. This is what you have to solve practically to get all the thermodynamic properties of integrable systems.
So I have a confusion. For quantum systems of Fermi or bosons, what is exactly meant by this R? Because this is the volume occupied by the system at asymptotic coordinates.
But here
is in terms of, I think, asymptotic states of the scattering theory. You have to think in terms of, instead of particles, so states that are related by scattering matrix in terms of wave packets, I think. But just, okay. No, just I want to. Now, is this clear? Now, do you have other questions, comments? No, okay. Then now we have all the formalism from thermodynamic beta-ansatz. We can compute eventually densities and currents. Now, for instance, if you take expectation value of a charge density, Qi, so I is the index of the charge, with respect to a state labeled by some set of beta parameters of inverse temperatures, like this, okay? So this beta here refers to this set of beta here, so this W, which identifies the state. Clear? So this, so we know that.
No more function of x.
At the moment, not yet, because at the moment we are still describing thermodynamics. Then when we do hydrodynamics, they will acquire also x and t. Good point. But first we need to have expressions for the homogeneous case, and then we apply local density. So this one, okay, we know that densities can be obtained from free energy by taking derivatives, right? Derivative with respect to the associated inverse temperature. Okay, right. Now, you start from this form here of the free energy, and we take derivative, and we should find this is chain rule, application of chain rule. Where essentially, when you take the derivative of this capital F with respect to beta, you take derivative of capital F with respect to epsilon times derivative of epsilon with respect to beta, so the chain rule property. And derivative of F with respect to epsilon, it's n, with a factor, I think, 2 pi, which comes out of the convention that we have taken. This factor 2 pi is always annoying, but it's a matter of conventions. But just to say, this is chain rule. Okay? Tuck, tuck. Yes, it's correct. It's fine. Now, do you all agree? Now we want to give some more expression about this one, and we can read it from here.
How is Qi derived?
This is partial derivative of pseudo energy with respect to the height Lagrange multiplier. Yes, and then I take the derivative inside here, and then this I write it like df, dx, dx, d beta.
That's fine. Why it's Qi?
Qi is the density, is the density associated to the multiplier I, because we want to compute densities to put it inside the Euler equation. This one, because, I mean, if you remember, free energy is like in thermodynamic limit, let's say. Something like that, right? Log of the partition function. Now, if you differentiate with respect to beta, you bring down this guy. And then there is an L in front, which gives you charge extensive divided by volume is density. It's standard StatMech, I would say. Now we write this object starting from this, and this we can write it. Again, we apply derivative with respect to beta I on both sides of the equation. Okay. And again, inside the integral here, we use the chain rule to take the derivative of this capital F. So compare this with this, where I differentiate left and right hand side by beta I, and for W we take this form. So when we differentiate by beta I, we take this HI. Okay? Now the good point is that for this d epsilon d beta, this integral equation is linear now, because you see, it appears here, but here it's linear. So this is a linear integral equation.
So you are doing this del epsilon del beta, right? In that equation,
Mm-hmm.
you get HI and then how you get, so enough Q you get by differentiating.
I mean, you differentiate with respect to beta. The derivative comes inside. Now beta is inside this one, right? And then I do df d epsilon d beta. And df d epsilon is this n. And now we define this object. I call it hi superscript dr, where dr stands for dressing. Yes. I tell you that this is always a mess. I do always a lot of stuff, mistakes with this. There will be others missing possibly in future equations. Okay. And what is the interpretation of this object? This dr means dressing. What is the interpretation? Let's say imagine that edge I, this is the bare single particle eigenvalue. Okay. Let's say, for instance, if you take I equal to energy, this is P squared over 2. So this term, if without interaction, again, you don't have this integral, and this tells you that the single particle eigenvalue is just given by the bare one. When you have interaction, you dress the single one free with the scattering events of all the other particles. So this is why it's called dressing. It's like this encodes in an effective way the effect of the interaction onto the quasi-particles by modifying their dispersion relation compared to the free case. Is it fine? Okay, then I think it's just a bit of formalism, just to conclude. And in particular with this, we can write then you see that if we use this object here, the epsilon d beta is this. This we can write it like this. Yes. Then now, in general, you see this is a linear integral equation.
So you are calling this del epsilon del beta as HIDR of
P. Yes, definition. This is a linear integral equation, so we can write it always something like, we can introduce some integral operator. This is like a convolution. So it's T applied to edge with the argument P is like a convolution over the index Q of this function. And with this, we can write this relation the following way. to invert it. So I'm just expressing in a compact way this form here. So it's the bare eigenvalue plus this operator here, t, integral, applied to the function n edge dressed. So where the application of this is essentially a function of p obtained upon integrating on the second momentum. And if you do this, you can invert this relation, and you can obtain the dressed eigenvalue in terms of the bare one by doing this inverse integral operator. When you solve this numerically, if you are disturbed by integral operators, you discretize over rapidities. This is like a matrix vector multiplication over the index Q. And essentially, this is like performing inverse of a matrix applied to a vector. Okay? It's like inverting a matrix in a linear system when you discretize.
T contains the 1 over 2 pi square.
Yes. Yeah. 2 pi, yes. Possibly there is still more. I think here and here. I just want to say that we use this because there is just one mathematical identity which I use, is that the integral, just to simplify a bit the expression, of a dressed function mathematical identity this is just an identity. This is proved in the notes. If you check the notes, there is a detailed proof of this statement. I mean, here we can take it as an input. In the end, it's just an identity. There is not much physical meanings in this, but it's useful to recast the expression in a way which has a nice interpretation. Thumb rule, when you have an integral over momenta of the quasi-particles, a generic dressed function g of the momentum, the occupation function n, times another function of p, essentially you can move this dressing to the other function as a thumb rule. This is proved in the notes. Now I don't prove it because otherwise we don't fit the time limits. But we can use it as where here, in the equation there on the top right, the one for Q. Yes? G is a function, generic function of momentum, and also edge. You take these as two functions, generic of momentum, n is the occupation function. Now we copy that. So I'm just copying the equation that is written on top. Here I am inserting a multiplication by 1, because we can do it. Okay. And now we can use this stuff here to essentially to move this here. Okay. And if you check here, this one, this is nothing but 1 dressed over 2 pi. Because you see the bare value is 1 divided by 2 pi plus the integral of this stuff, where here there is a 1. And this, therefore, using this relation here, we can write it as one dress over 2 pi is rho total and the rho total times n is rho p. And this is exactly the expression that we need. We are almost done. 20 minutes, yes. And see, this expression has a very neat physics interpretation, because you see that the charge density essentially integrates over the density of particles in momentum space, so it counts how many particles with a certain asymptotic momentum there are in your state. Each one carries a bare quantity for the charge of interest, which is Hi of P. Right, it's pretty natural. And this is exactly the expression that we need. And notice that here the state is identified one-to-one by the multipliers, or in an equivalent way by this density of quasi-particles.
So what did you do in the last line? I understand this is rho total in Hi.
I mean, I bring dressing here. This is one dress over 2 pi.
In the last line,
Okay, this is rho total times n, and you read it from here. N times rho total is rho p. And the state is identified by the multipliers, or equivalently by the root density. It's an equivalent set of coordinates, so if you give me this function, you can uniquely identify all the expectation values of the charges. Okay, so this object, essentially, the magic of integrable models is that you have many charges in principle. This index I runs over an extensive number, but they all are encoded into a single function, which is this rho p, which is identified by the scattering basis. So this tells you why the scattering basis is super efficient, because all the complexity of the GGE, of the state, all this information about a microscopic number of charges, in the end, it's all compactified, zipped into this function, which you can get for thermodynamics out of a set of nonlinear integral equations. And now we need the last bit for the last, I think, 20 minutes. Remember, in the Euler equations, we have this stuff. Right? Where these expectation values are taken over a Gibbs or generalized Gibbs state. Now, this guy here, now we wrote it. We obtained a nice formula. We miss this one, the current density. And this is the last stuff that we do for today, so that we can complete the derivation. Now, for the density, you see this follows quite natural from the thermodynamic Bethe-Ansatz. Yeah, please, don't worry, don't say sorry.
Yeah, so this Qy beta average, thermodynamic average is depending, so it depends on the single particle level H.
Yeah, this is, if you want to know, for instance, the density of particles, particle density, you put Hi equal to 1. If you want the energy, you put Hi equal p square over 2.
So
Yeah.
all the information of the scattering, so particles are scattered and getting out. So all the information scattering are captured within this row.
Exactly, rho p inside has all the information because it comes out of this machinery of integral equations where there is the scattering shift. And the rho total accounts for the change of volume due to scattering. So this density is dressed by the wall interaction, by the medium where a quasi-particle propagates, which is an interacting medium because it undergoes collisions.
Right, and there I guess the other single particle levels are also important, this H's, which is not...
What?
If you're looking at the ith charge, then the other quasi-particle level, other levels are also important, like H's.
Yes, yeah, but because, I mean, rho p is a function of momentum.
Right.
But to solve it, each momentum p is coupled by the other momenta. The equation is not local in momentum.
Right.
This is because a momentum p interacts with all the other ones. This is where the interesting point. So indeed, in integrable models, excitations are collective, because when you insert a particle, all the others rearrange as a consequence of the interaction. So if you insert a particle with a certain velocity, the excitation you are adding is not equal to that velocity, like in a non-interacting system. It's that velocity dressed by the rearrangement of the whole sea of the other particles. This rearrangement involves interaction among all the momenta, and this is why these equations are non-local in momenta, because they account for all these scatterings. Now we need just this guy. This guy, it's more difficult. Yes?
I can keep with the tracing you did. The 1 ER divided by 2 pi gives you root. How did it?
What?
1 by 2 pi, how did it give you root?
I'm saying that 1 dressed over 2 pi is equal to rho tot. Because you see that, rho tot is 1 bar divided by 2 pi, and here there is a 1. Now, this object is more difficult to compute, and it has, this doesn't follow immediately from the thermodynamic Bethe-Ansatz description. One requires some argument. Indeed, in the original papers where it was derived, it was not actually derived. It was guessed on the basics of a physics argument, let's say. It was later derived. Now I will provide the one argument that was provided in one of the original references. Then I will write also the references. Now, let's say, where do I am? Here. This argument applies to relativistic systems. So, argument for relativistic systems. So the argument goes as follows. So for a relativistic system, you use what is known as crossing symmetry. Crossing symmetry essentially tells you that for a relativistic 1+1 dimensional field theory, you can swap space and time. Okay? You can look at scattering in the direct channel or in the reciprocal channel. But it means that essentially swapping space and time means that if you have the space-time point xt, this you can map it to minus I t I x. And under this change, if you take the quadrivector or 2-vector in one dimension of the density and the current, this goes into this way. So a density is mapped into a current, and a current is mapped into a density upon swapping space and time. Okay? If you do and in particular, if you have momentum and energy, this is like the relativistic notation where this is the space component P, E is the time component, this is time component, this is space, and this is space-time. This one goes into.
So here this levels recharge are no longer quadratic, they are linear, right?
What?
Here you cannot write H as p square by twice, right? It's linear.
What? Where? Here? This is the bare one. This is the bare one, but because this is the rest.
Right, so bare one is not quadratic, that's what I'm thinking.
Bare one is an input, is like p square over 2. It's different. I mean, for a relativistic system, for instance, you have a different parametrization. For instance, you have that the momentum depends on the rapidity, is something like that. So that when you do for a relativistic system, these, for instance, are the bare eigenvalues. So they are parameterized in terms of what is known as relativity rapidity, so that when you have E square minus P square, this is the Einstein relation for a relativistic particle of mass m. It's a different parameterization, but the formula still applies. There are also integrable field theories that are integrable by Bethe-Ansatz, for instance, Sinch-Gordon or Sine-Gordon as well. Just to say that this applies also to relativistic integrable models. Modulo that you have to change these inputs here. And if you do this, you have this swap. Now, you see that upon doing a crossing symmetry, which apply for relativistic field theories, you swap essentially densities and currents. So the argument is that the argument is nice because it doesn't require too many calculations, and the result at the end is nice. So if for densities you have a free energy whose derivatives generate expectation values, then if doing crossing symmetries, densities and currents are swapped, there must exist also a free energy flux function, let's say, of the multipliers, such that one can obtain currents taking derivatives of these. Okay. Okay, we have 10 minutes, we can do it. So this G is to the currents what F is to the densities, because we saw before that, for instance, for densities we have this. Notice the similarity between the two, okay? Now, if currents and densities indeed map to each other under this crossing relation, they must be treated the same way. And therefore, there must exist also a function G that generates currents. For instance, in exercise 1 of the tutorial, you are also asked to construct this function for the case of the ideal gas, to make it concrete. Now, if you have this, what is this G? Again, we compare with this one. So, for densities, they are associated to momenta. Currents are associated to energy. Sure, of course.
For the relativistic case, the crossing symmetry is okay. But can we do this to non-relativistic systems?
Of course, no. This argument, crossing symmetry, is only for relativistic system and is an argument to justify the formula. Then the formula turns out is valid also in general. At the beginning, this was a guess, so it was not a proof for the case without relativistic.
Did you find any proof of this?
Then there are some papers that I can show at the end later, some years later. This was done in 2016. I will write the reference. I think 2020 there are papers that have established this for Toda chain, also for XXZ, etc., for non-relativistic. But yes, this argument applies only for relativistic. That's correct. Then this G, of course, you see currents are related to energy because currents are intrinsic non-equilibrium functions, no? Because they flow in a certain direction. And the energy, of course, is the generator of time evolution, is what gives you, is what is associated to time in physics universally. So in principle, this G is obtained from dF by changing the integration measure from momenta to energies. So you see, instead of dP, we have dP E prime, where E prime is derivative of energy momenta, so it's d epsilon. So it's an integration over the energy measure, because energy is associated to time evolution, which is associated to current. And this is also why currents do not immediately follow from thermodynamic bad answers. Thermodynamic bad answers tells you equilibrium fluctuations. Currents are intrinsic non-equilibrium objects associated to time, to flow, which is not an information there in the Gibbs state. So you have to invent something else to guess a form. And now if we have this, we do this minus dg d beta. Give me just 5 minutes because we started 5 minutes later, so that I close symmetrically. And we explain. So we do minus dg d beta over this function here. And we get this. This is also something that my supervisor was always telling me. When you write equations, be tidy and align them vertically. Very important. this is fine, right? So I'm just taking the derivative inside and I use again chain rule, possibly taking all the 2 pi factors. Now again we use the relation that we saw above where we can move the dressing from here to here, okay? And we obtain this one. Now, remember again that n is particle divided by total, okay? So I can do here.
Just a query. You told that this, for this identity that you have written, I can change the dressing part. So it doesn't depend on the functional dependence of the occupation?
No, the important point is that you have n and then 2 generic functions. So the functional form is just that you have n inside the integral and then 2 functions, whatever they can be. No, it depends that n must be the occupation function. So it must be this object here. So n is not arbitrary. It must be the occupation function. The other 2 functions can be arbitrary. I think in the notes there is the proof, and we can also discuss it later if you want, so that you can understand it better. Unfortunately,
some self-conjugate function or something like that is required or not?
What?
Those 2 functions?
No, they can be whatever. They are arbitrary. You don't need the constraints on them. Now, this one we can write as maybe I have also a factor 2 pi somewhere. Cazzo, fuck the system. Okay. I'm dividing by 1 dressed. Then I multiply by, no, it's not there, it's correct. I multiply by 1 dressed, so multiply, divide by the same factor, and then 1 dressed over 2 pi, it's rho total, and rho total times n is rho p. Is it okay? Maybe I write it explicitly. Let me do 1 step more. Are you convinced? Okay. And now you see that, so here you have density of particles, bare eigenvalue, and then what is this object? This is derivative of energy with respect to momentum, divided by 1 dressed. 1 dressed, let's say we could write it something like this. Because the derivative of p with respect to p is 1, okay? So this is an identity. And therefore this we can write it as this. Yes, just let me finish the argument and then, please ask.
No, 1 dress, how is writing is rho prime?
I'm saying that 1 dressed.
dp by dt is 1.
Yeah, exactly. Here I'm just saying that dp So I write this as the derivative of the bare momentum with respect to bare momentum itself. Dressed. Yeah, this is a P, sorry, maybe it's not clear. And now imagine you have energy that, for instance, is something like this, the bare. So E prime is P. So this is velocity divided, so it's momentum divided by something like mass, P prime. So it's a velocity. Not surprisingly, this you call it effective velocity. And there is a 2 pi. And indeed, this has the meaning of is the velocity that you see. It's let me write it where here. And this object is the velocity but dressed again. So it's not the bare one, but it's dressed by the effect of interaction. And this has the very simple form, interpretation of a current. Density of quasi-particles times the velocity, so it's the flux at which they move, times the quantity they bring, the single particle eigenvalue. And I have finished the blackboards. Maybe yes. And now we have all the ingredients to write down the final equation, because we have expectation of densities and expectation of currents. So we have because now if you want to describe a weakly inhomogeneous system, now it's where the space and time enters, finally. You upgrade this function as space-time dependent expressions in the thermodynamic expectation. Thermodynamic expectation is the one that we derive above, for instance, the effective rho p edge. We plug it inside here for current and density, and we get this. This is partial derivative in time of rho p plus partial derivative in space of velocity effective times rho p. And since this basis here is arbitrary, because I can choose an arbitrary basis for the single particle eigenvalue, if this integral is 0, it means that this guy must be 0. And this is the final equation. And I want to write the references. Oh, we are done.
So that data includes zonal acidity, is it?
Hmm?
Data.
No, it's not that Bertini. It's Bruno, it's not Lorenzo. That one is another one. But these are just the two references where this was originally derived. In this work here, this is where this argument with crossing symmetry for the currents is done, where I took it from. And in both these papers, which are simultaneous, they end up with this equation. This is the fundamental equation that we will solve in the next one. And I just want to emphasize one important point, is that you see for integrable models, this index I of the charges runs over an extensive number. So in principle, one could say writing their hydrodynamics is an hopeless task because I should write an infinite number of equations, one continuity equation for each conservation law. But the point is that you have this scattering basis, which is particularly clever because it encodes, it compactifies all charges in terms of a single function, which is this rho. And then if you write an equation for rho, you have all. It's like one to rule them all, more or less. And you get this. And this is like Euler scale generalized hydrodynamics, is called. And it's the fundamental equation, and next time we do a couple of applications of this.
The local quantification in the phase space.
Yeah, if you want so. If you want so. It's like a convective transport of hydrodynamic modes. Next time maybe I build some additional physics explanation of this, but at least we concluded with that. And yeah, in the notes you find also some additional explanation about the effective velocity that today I have cut because of time. Please.
To go from the integral equation to the box adaptation, you need the HI cover the
You need the
complete set.
you need to exactly. This is an important, a very important point. You need completeness of the charges, and actually you can show that these charges, the edge IP, they satisfy an orthonormality relation with a scalar product properly defined, and therefore they are a complete set. And in particular, for them to be complete, you should include both the local charges and what are known as quasi-local. The local are the ones, this is more technical bits, are the ones that are obtained by derivative of transfer matrix, like Chiara explained. Quasi-local are additional kind of charges. If you put all together, you have a complete set, and then this step is justified. This is discussed in these two papers, they discuss these aspects. And just to say, it's called the generalized hydrodynamics, GHD, because it's an hydrodynamics, HD, but it's based on a generalized Gibbs ensemble with multiple conservation laws. The standard hydrodynamics, let's say, is based on 3 conservation laws. Here, so Gibbs ensemble, here generalized Gibbs, multiple, generalized hydrodynamics. This is just the origin of the name. That's it.
Any more questions? Yeah, if not, let's thank the speaker.